Hydrogen bond is a kind of very specific type of intermolecular interaction. So from your high school or your general chemistry, we know that water can have a strong hydrogen bonding. So a very important point is why we call this as bond, not hydrogen force, not hydrogen interaction, but we call it as hydrogen bond. So we have to look at the origins or the basic background of the hydrogen bonding. Okay. So we may consider almost every intermolecular interaction as electrostatic force. Right? So if you think about the hydrogen bond in terms of electrostatic force, you have to find the positive and negative pole of the water molecules. So as you can see, we have hydrogen, which is very positive because of the En value of hydrogen and oxygen is so far apart from each other. And then we have negative charge on oxygen, and the area that contains a negative charge of the oxygen is an electron cloud. And because you have two electron pair on the oxygen atom, right? So the interaction should happen between positive charge hydrogen atom and the electron pair of water. So we have this kind of interaction. So positive charge hydrogen and negative charge of electron pair come up together and creating what is called hydrogen bond. So as you can see, the very important criteria to have hydrogen bond are two things. The first thing is that partial positive hydrogen atom. This is because your hydrogen is bounded with very high En atom. So as you may know, the very high En atoms are the highest is fluorine, and then oxygen, and then chlorine, and then nitrogen, right? FOCl and N, these four are the topmost high En value atoms in the universe. Then the other things that you need or require is the electron pair. But as you know, that not every atoms can have hydrogen bonding with the positive charge hydrogen atom. And from your high school, you always remember that FO and N, three of this element, can have hydrogen bond. This is because FO and N is in the first period, right, which is small enough. Because you may know, as I mentioned very frequently, that the electronic potential energy depends upon the charge density or electron density. So if you think about the negative charge, right? So the high electrostatic potential energy, it depends on the electron cloud, right? The density of electron cloud. So that means if you have one pair of electrons comparing this series, fluoride, chloride, bromide, and iodide, right? The highest energy level is fluoride because you have very small atom and it's grow bigger from top to bottom, right? One negative equally, but yeah, you have very small area for fluoride ion. So that means the electron density or the charge density is the highest. Comes to the potential energy of the fluoride is higher than chloride, bromide, and iodide. So with higher negative potential energy, it can then react or interact with positive hydrogen atom. So electron pair have to be the electron pairs of second period element F, O, and N. So you have to meet with these two criteria to construct the hydrogen bond. Okay. The thing that I want to another thing that I want to mention is if we talk about ion dipole interaction, for example, which is stronger than hydrogen bonding because it's really charged, right? It's a cation, anion, things like that. So if you dissolve sodium ion and chloride ion with the water, so the water come around your sodium ion like this. As you can see, you have no such a well-organized system, right? The water just randomly comes together with your positive and negative charge in every direction, unlike hydrogen bonding. As you can see from my hint, I draw it according to the bond angle and bond length and everything. So as you can see, you may know that the tetrahedral structure adopts 109.5 degrees roughly for the bond angle and everything here, right? So roughly this is 100 and something degree, right? This is because of the VSEPR, valence shell electron pair repulsion. So if you have 4 groups of electron clouds, then they have to stay away from each other as far as possible, right? So it's 109.5. But for hydrogen atom over here, you have 2 clouds of electrons. The first group of electron is the covalent bond between H and O on the water molecule. And the other group is this electron pair, which is now have interaction with H. So H is now surrounded by 2 of electron clouds, 2 of electron pair, and they have to stay away from each other as much as possible. And as a result, you have the bond angle over here about 180 degrees. Right. So as you can see, we have bond angle. And we also have bond length, because OH bond here in the in covalent molecule, common covalent molecule OH bond is about 1 angstrom, and this is about 2 angstrom. So we can say that is about maybe half of the strength of OH covalent bond, normal covalent bond. So because if it is actually electrostatic, it has to come in any direction. But this is not because of the only electrostatic. You have bond angles. This gives you a hint that there have to be some kind of orbital overlapping, orbital interactions. So you have this kind of bond angles. Okay? So if I want to show you more, deeper in details, even deeper in details, we call this hydrogen bond because you're creating a covalent bond. Why? This is positively charged hydrogen atom because of the En here. So this is electron poor hydrogen atoms. So you have interaction with this. So when your hydrogen, the electron of hydrogen atom was taken away by this oxygen, right? So this hydrogen requires 2 electrons in order to fulfill his K shell, right? So if 2 electrons was taken by the En of oxygen, these hydrogen atoms have to find 2 electrons, other 2 electrons, in order to fulfill his K shell. So what happened is, this hydrogen bond is turned out to be coordinate, covalent molecules, bond. So by this coordination, as a result, your water molecules is changed to be this one, which you may very, very familiar with it. This is called the hydronium ion. Oxygen atom is turned out to be 1 positive because you lost electron to your hydrogen atom here. And this is hydronium ion. As you can see, this is a chemical reaction. You turn the water molecules to something else, hydronium ion. And this hydrogen bond is now changed to be a covalent bond, simple covalent bond here, right? And as a result, your oxygen atom now contains 3 electron pair, and the charge of your oxygen atom is 1 minus, because this oxygen atom takes 2 electrons from the bond back to himself, right? So that means 1 electron is come from hydrogen atom, no? So this oxygen contains extra electron and turn out to be 1 minus. So if you have to look, if you look at this pair, as you can see, H is still attached to very high En oxygen. So this H is very positive because of the high En, right? And you now have electron pair on the hydroxide ion over here to be named. So you still have hydrogen bond between hydroxide and the hydronium ion. And as I said, that actually hydrogen bond is a coordinate covalent. So this hydroxide coordinates electron back to the hydrogen atom of the hydronium ion. So if hydrogen atom now fulfilled his K shell with 2 electrons, so this 2 electron is not necessary anymore. So he returns this 2 electron back to the oxygen on the left-hand side, and then your system switched back into the original state to water molecules. So as you can see, this is an equilibrium between water and hydronium and hydroxide. And we called decay here as the water dissociation constant, Kw. So as you can see, this is called hydrogen bond, not hydrogen force or hydrogen interaction, because hydrogen bond is a covalent bond. Hydrogen bond is a coordinate covalent and turn out to be just normal covalent bond at the end. Okay? So if you look at this, you may consider that 180 degree because you're constructing a new bond. Right? So if you want to constructing a new bond, that means you have orbital overlapping. So if you have orbitals interaction, you call this as bond. Okay? So this is the donor, right? The left-hand molecules is the donor. We call this as electron donor, but we call this as hydrogen bond acceptor. Okay, it's electron donor, but hydrogen bond acceptor because he accepts electron from the other oxygen, right? So electron donor gives away electron from the valence shell, right? And the valence shell of the molecules is not called the valence shell. We call the valence shell of the molecules as HOMO. So electron donor using HOMO to explain the interaction. And this one, electron acceptor, right? So think about the shells, electronic shells, right? So we have electron field in the shells. So if you want to put extra electron into your molecules, right, you have to put it on the empty orbitals, right? And the empty orbitals, which is closest to the nucleus, right, with the lowest energy state. So this is called the LUMO. Right? So next water, the second water molecules using LUMO to interact with this one because it is an electron acceptor. So you have to think about HOMO and LUMO of the water. And actually, if you know the structure of HOMO and LUMO orbitals, you can see clearly how they interact, which kind of angles they manage to interact with each other. So hydrogen bond is this deep. Okay? It's not just an ordinary electrostatic force between positive and negative, but it is actually an orbital interactions. And because it is the orbital interactions, so we call this as bond. Okay? Hydrogen bond not only used for describe the dissociation of the water. We can use to describe the dissociation of any acid or base, right? So if we change the water on the left hand to be ammonia, NH3, with the same kind of interaction, you end up with the ammonium ion, for example. Or if you change the water molecules here with the chloride, with HCl instead. Okay. with HCl. Right? So this HCl, H is very positive again, because Cl is the third most highest En, right? The third highest En element in the world. So H plus hydrogen atom here is very positive. So after you have interaction here, hydrogen fulfilled his electrons, his K shell with electron here. So he returned electron back to your chlorine atom on the right hand. And at the end, instead of chlorine atom, you end up with the chloride ion. But anyway, chloride ion, unlike hydroxide, oxygen atom is in the second period, but chloride ion is in the third period, so it's huge. That means electron clouds is loosely packed around chlorine atom. Right? So the negative charge is not very negative, it's not very high energy in terms of electronic potential energy. So you cannot create, or you can create just a very, very weak hydrogen bond out here. So that means interaction here is weak, so it cannot turn back the equilibrium. Equilibrium go forward drastically because on the left hand you have a strong hydrogen bond, but on the right hand you have weak, very, very weak hydrogen bond. So as you may know, that water dissociation constant is 10 to minus 14, but for HCl is the strong acid. So if it is strong acid, you can approximately say that the dissociation to the right hand, the equilibrium here is about 100%, but actually you have Ka. The Ka of this one is equal to 1.2 times 10 to 6 plus 1,200,000. Okay, this is the Ka of the HCl. So we can approximate that the HCl dissociate for 100%, and we claimed that the HCl is a strong acid. So this is the basic background of the hydrogen bond, which is very important. So now, from this kind of explanation, you may now look at the hydrogen bond in completely different way comparing with your high school, right? Is the bond because of the intermolecular because of the orbital interactions. Is the HOMO dominate electron to the LUMO, sigma star of the HCl, right? So as you know, the sigma star here, orbital shape pointing towards the oxygen, towards the left hand side 180 degree to the bonding axis. No. So you have to think about the molecular orbitals of HCl and everything. So we can describe by look at the sigma star orbitals and the HOMO and LUMO and everything. So this is the clearer picture of hydrogen bond. Before we end our hydrogen bonding, I want you to compare two of oxyacid. The first one is called hypochlorous acid, and the second one is called perchloric acid. Hypochlorous and perchloric, which one has higher EA, or which one is a stronger acid? So you have to explain this using hydrogen bonding system, okay? So the picture over here is the acidity of HCl explained by hydrogen bond. But now I want you to compare these two. So constructing almost exactly the same as this one, but you change the acid from hydrochloric to these two, okay? And then explained by comparing with the strength of hydrogen bonding and everything, you then can have the answer which one has higher Ka. Okay, so I will let you do this by yourselves and then see you in the next video for the correct answer.